Yeah, so this is our last keynote speaker for the day. It's my pleasure to introduce Professor Anirudha Majumdar, and he is an associate professor in mechanical and aerospace engineering at Princeton University. He also has a part-time visiting research scientist role at Google DeepMind. He received his PhD in DS at MIT, and then BS from UPenn. Outside of the formal introductions, it's a pleasure to see you here after, especially in LA, where I am now, because Ani was my postdoc advisor. So I was in Princeton a year ago. So really looking forward to this new work and learning.
Cool. Yeah, thanks so much for the introduction and the invitation to present here today. So I'll be talking about some work that I mostly did during my sabbatical at Google DeepMind over the past year on predictive red teaming. I'll say a bit more about what that means. So I think at this point, we're all kind of used to seeing videos like this, videos where we've trained a manipulator to do some kind of text-based task using behavior cloning, so typically some kind of diffusion policy-based approach. And if you play around with these models, what you often see is that we can get pretty strong nominal performance, the performance in environments that are similar to what you trained your robot with. But if you change various kind of factors in the environment, if I change the distractors, change the lighting, change the table texture, that can result in really large degradation in performance. And we see this not just with kind of single task diffusion policies, but we see this with policies that have been trained on much larger amounts of data as well. This is the OpenVLA model. It actually works zero-shot without any fine-tuning in our lab for these pick-and-place tasks. But as soon as we add even just a handful of distractors, that leads to a severe degradation of performance. So going from basically 100% performance on this pick-and-place task to about 60% performance. Another example, more recent, this is the Pi0 model that we took and fine-tuned in our lab. And again, works kind of beautifully in the settings where we collected data for fine-tuning. But as soon as we change the lighting conditions a little bit, that leads to a severe degradation in performance. In this case, it's actually the fine-tuning that's broken the generalization. The base model, it has more generalization, but we fine-tuned it for this specific embodiment, and that has degraded the generalization of the policy. So the question that I was interested in, that we were interested in here, is something that I'll call predictive red teaming. And I'll say more about where that name comes from. But basically, the goal is, given access to nominal data, so given access to the training data for your policy, what we want to do is find vulnerabilities of the policy with respect to different environmental factors. So if I change the background to a different color, how much is that going to degrade performance? If I add a distractor that maybe requires the robot arm to move a little bit, how much is that going to degrade performance? If I change the lighting condition into some kind of harsh blue lighting, how much will that degrade performance? And the goal here is to do all of this without performing any hardware evaluation. So hardware evals are hard, and we want to be able to make these predictions without doing any kind of real evals with access just to nominal observation. That's what I'll refer to as predictive red teaming. And there are kind of two versions of this problem. So one version is where you want to rank environmental factors by performance degradation. So you want to be able to say, if I have blue lighting, that will degrade performance more than red lighting, which will degrade performance more than adding distractors, and so on. So you want to rank different factors. The other kind of formulation is more ambitious, where you don't want to just rank the factors, but you also want to predict the absolute degradation in performance away from the nominal performance of your policy. So let's say the nominal performance in kind of conditions similar to what you trained on is 90%. We want to be able to say, if I change the lighting, that's going to result in a 30% reduction in the success rate. So yeah, this term red teaming actually originated in the military realm. So red is coming from the Cold War, so around the 1960s. People did these exercises where there would be a team that focused on how to break some kind of military strategy. More recently, that's expanded to cybersecurity, and even more recently, red teaming for LLMs is a kind of really vibrant research area. LLMs and other kind of generative models. Red teaming for robotics, I think, is in a much more nascent stage, I would say. There's some recent work on looking at instruction generalization. So if I change the prompt that I give to my robot by a little bit, can I find some semantically identical prompt that will degrade the performance of a language instructed robot? So that it's a little bit different in terms of focus. Like here, what we're going to focus on is not just instruction generalization, but generalization to other environmental factors. There's also some work on jailbreaking, which is kind of similar to instruction generalization, where you want to find some way of prompting a robot that will result in it doing something potentially unsafe. There's also a lot of work on simulation-based testing. So using simulators to predict the performance of your policy in nominal conditions and also other conditions. I guess we were just chatting about this offline. I think some people have had some success in simulators that are predictive of real performance, but often takes a long time to develop a simulator that is reflective enough of real world performance. And in our own group, we've spent kind of many months trying to do this and have had mixed success. So what I want to do, I guess what we wanted to do here was have a much more lightweight approach that doesn't require real world evals, doesn't require simulation-based testing. And the main kind of hammer that we used is progress in language instructed generative editing. So if you haven't played around with these models, they're definitely worth kind of trying out. We used Imagine 3, which is from Google. And basically, the way this works is you can take some nominal observations, and you can say change the lighting, change the color, add a person, add some kind of a distractor object. And you can make very precise, targeted, and photorealistic edits to your nominal observations. And once you've done this, so once you've taken this bank of nominal observations, edited them, we use a kind of failure predictor in the form of an anomaly detector to predict the degradation in performance that will result from each of these changes. So just to give you a sense for what this kind of image editing looks like, this is an overhead camera view. This is a wrist camera view. And you can do things like, say, just via language, change the background to green, add a black trash can, add a person by the table, change the lighting to red. And you can, again, kind of make these pretty precise and targeted edits to the observation. And once we make these edits, the next step is to predict how much the performance of your policy will degrade for these different environmental changes. And the way we do this is a really simple, maybe one of the simplest kind of anomaly detection methods, based on looking at distances in policy embedding space. So you have your bank of nominal observations, you pass that through your policy, you compute some latent kind of embedding like feature that comes from some middle layer of your policy, and you compute that for all your nominal observations. In this work, we were looking at diffusion policies in particular, and what we found to be quite effective is to look at the latent embedding right before the denoising steps. So that kind of encodes the instruction, it encodes the visual observation as well. So once you've computed these embeddings for the nominal observations, you can also compute embeddings for the edited observations, so for the distractor, for instance. And you look at how far away these edited observations are from the nominal observations in this kind of latent embedding space. Specifically, we're looking at cosine distance, which is kind of commonly used in self-supervised learning. And yeah, that's kind of the rough idea. And the intuition is that if your embedding is far away, that looks different to your policy compared to nominal observations. So maybe your policy is not going to succeed. If it looks similar to nominal observations, it will succeed. That's just kind of rough intuition. Ultimately, if we want to predict success rates, what we need to do is find some threshold to say this is an anomaly, this is not an anomaly. We use conformal prediction in this work, which basically roughly corresponds to matching the anomaly rate under nominal conditions with the failure rate under nominal conditions. So we're kind of trying to create this equivalence between anomalies and failures, and we match those two rates under nominal conditions, which we assume you have data for. And then for each environmental factor, what we do is compute the proportion of anomalies for that factor. I'll call that alpha F. It depends on the policy pi as well, because the embedding comes from the policy. And then you just predict the performance of your policy for some factor as 1 minus the anomaly rate. So yeah, basically the anomaly rate is acting as a surrogate for the failure rate when you make these different changes to the environment. And like I said, you generate these edited observations for each factor, compute the anomaly rates, and 1 minus that is the prediction for your success rate. So yeah, super kind of simple, lightweight, computationally efficient approach. So to validate this, we did lots of hardware experiments. Ultimately, we want to see how good are these predictions from this pipeline when you compare them to real-world evals when you change these different environmental factors. So we looked at 12 environmental factors, so 3 background conditions, 3 lighting conditions, 4 kind of specific distractor types, a person that's close to the table, and also changing the height of the table. And we also looked at 2 kind of diffusion policies that ingest RGB images. So the first one combines diffusion with kind of classical trajectory optimization methods. The trajectory optimizer predicts the waypoint, and the diffusion fine-tunes that. And then we also looked at just a vanilla diffusion policy. And what we found was, so actually maybe let me just explain what this plot is. So for each environmental factor, we made these predictions based on the image editing pipeline. And then we also kind of physically instantiated that and did hardware evaluations to estimate the real success rate. And then we ranked the different factors by how much impact they had on the performance. So the y-axis here is the real estimated rank based on real hardware evals. The x-axis is the predicted rank based on 0 hardware evals. This is kind of image editing plus anomaly detection pipeline. And what we found was a really pretty strong correlation between the predicted and real ranks, kind of as quantified by the Spearman rank correlation. The more kind of ambitious version of this is not just ranking different factors, but actually predicting the absolute success rates. And again, this is comparing the real estimated success rates from hardware evaluations to the predicted success rate. And again, we found a pretty strong correlation between the two. Similar plots for the kind of vanilla diffusion policy. So again, strong correlation in ranks and reasonably strong correlation in the kind of absolute performance of the policy as well. So I guess there are a few reasons you might want to predict what will degrade the performance of your policy. One is if you want to deploy your robot somewhere, it's useful to know, like, is it likely to fail or succeed if I change some environmental conditions. I think maybe the even larger use case for this, the more kind of important use case for this is not just finding vulnerabilities, but also patching them by adding more data. So the way we did this was we collected some additional demonstrations for the factors, the 3 factors that were predicted to degrade performance the most. And we just go fine-tune the original policy with the original data and also the new data, the small amount of new data that we collected. I guess as you would expect, performance is improved by quite a large margin for the conditions that we collected data for. So we saw kind of improvements between a factor of 2 and a factor of 7. I think what's even more interesting is that we also see some signs of cross-domain generalization. So if you collect data for, let's say, blue lighting or red background, that additional data also helps pretty significantly with factors that we didn't explicitly collect data for. And yeah, that's kind of what this plot is showing. So improvements not just for the 3 factors that we collected data for, but also for the other factors. So yeah, I guess the paper is up on archive. Feel free to check it out, and I'm happy to take questions on that. What I want to do, I guess, for the remaining maybe 10, 12 minutes or so, is that how much time we have roughly? Okay, good. Is to dig a bit deeper into this question about data collection. So if I know kind of what will degrade my policy, or if I know that something will degrade the performance of my policy, how do I improve it by adding some additional data to fine-tune my policy? And this is the second paper that I'll talk about. This was work led by Lihan, the first year PhD student. He's also around in the conference, so I guess feel free to catch him. So I mentioned this kind of simple approach that we used in the previous work, which was to collect some data kind of greedily for the factor that leads to the greatest degradation in performance. One challenge with this is that this approach overlooks the fact that different factors might just be intrinsically hard. So maybe there's some particular sensor on your robot that doesn't give you full information about the environment, which then kind of impedes generalization along some particular axis. Yeah, if you just greedily collect data for the factor that leads to the greatest degradation of performance, you're not taking into account the intrinsic difficulty of factors, and also the interaction between factors, like the fact that if I collect more data when I change the lighting, that might actually help me generalize not just lighting conditions, but also different table texture conditions. So another kind of simple approach is just equally collect data for all factors. And this is also not super efficient because it fails to prioritize what factors lead to the greatest improvements in performance. So what we want to do is somehow figure out what factors will lead to the greatest kind of overall success rate improvement. So overall across all the factors that you care about. And so the question becomes, how do we know what the factors are to prioritize? Question?
Sorry, a quick clarifying question. What do you mean by intrinsic difficulty again? Can you go over that?
Yeah. So what I mean is, so I guess maybe just to give you an example, let's say I'm looking at like generalization to different. Let's say I'm like opening a closet or something like that, and I don't have a camera that has a particularly good view of the closet. So maybe my like a humanoid robot, I'm looking just down and the closets are up high. So I have some partial observability there because of the sensors. So if I want to generalize to variations in closets, let's say maybe that's one of the factors that I really care about, that's going to be just intrinsically hard because of the partial observability that's coming from my sensor. So that is, there's no point collecting more data when I vary that factor because it's just hard because of the embodiment of the robot.
It's more of a, like esoteric.
Yep. Yeah, exactly. Yeah. So the approach that we took here was based on a scaling analysis. So we call these factors scaling curves. And the rough idea is to try to plot the improvement in performance that you get as you scale data along a particular axis. So if I collect data where I change lighting conditions, I can train different policies that use different proportions of my data that various lighting conditions. And I can evaluate those policies and see how much is my performance improving as I add more of a particular kind of data. And then I can kind of extrapolate those curves and figure out what will lead to the largest improvement in performance. So yeah, I guess this is just kind of visualizing what I said. You look at one particular factor. Let's say you're looking at distractors. You look at all the data where distractors are varied, and you look at different checkpoints that are trained with different proportions of that data. And on the y-axis is the average kind of overall success rate across all the different factors that you care about. And what we do is predict the performance kind of improvement that you're going to get by fitting a power law curve to these kind of data points. And if you have some data budget, then you predict how much improvement you'll get if I collect more data along this particular axis. We do this for each of the different environmental factors, and then we can kind of rank them by the expected yield in improvement if I scale data along each of these. I guess the kind of final step is just scaling your data along the axis that was predicted to yield the greatest improvement in performance. So yeah, I'll show some quick kind of experiments. This is a single task diffusion policy that's been trained on this pick and place task. The nominal performance is about 90%, kind of as measured by hardware evaluations. There's a large degradation in performance when you change various factors like the robot initial pose, the object pose, table texture, and so on. And if you just equally distribute your data budget across all the factors, then you can regain some of the performance. You get back to about 60% success. But if you do the scaling analysis to figure out what data we should prioritize, you can essentially get back up to the nominal performance, even with these changes in environmental factors. We did this also for a larger model. So we took the Pi0 model and fine-tuned it on a couple of different tasks, like folding a towel, putting an object in a drawer. And again, you see something similar: strong nominal performance, large degradation in performance when you change different factors. You can get some improvements when you equally distribute your data budget, and much larger improvements when you prioritize data collection using this scaling analysis. This is just kind of showing more quantitatively what the results are like. This is the zero-shot performance if you don't add any data. This is the kind of equal spreading out of your data budget. This is what happens when you use the previous strategy that I had mentioned, where you just look at what factor will degrade performance the most, collect data for that factor. We also used a data weighting scheme remix, which uses a distributionally robust optimization to figure out what weights you should put on data that you've already collected. But that doesn't necessarily tell you what data you should go out and collect more of. And yeah, I guess that's kind of where the scaling analysis comes in. It tries to predict what data will lead to the largest improvements in performance. This is visualizing the curves. I guess one thing I should mention is that each of these points is constructed using around 15 hardware evaluations per point to construct the scaling curve. And we found that the scaling curves, even with a relatively small number of evaluations, once you extrapolate them, they're pretty predictive of the actual performance that you get when you add that data. And in the paper, we have kind of multiple hardware experiments and also a bunch of experiments in validating these scaling curves. One major challenge with the approach that the way I presented it is that to construct these scaling curves, you need to do a lot of hardware evaluations. So 15 per point, there's a bunch of points, there's a bunch of factors. I think this makes sense in cases where evaluations are cheaper, much cheaper than collecting data, which is true in some settings. But yeah, doing hardware evals is challenging. So what we were interested in is, can we find some proxy metric that was predictive of the real success rate? And I guess kind of taking inspiration from the first part of the talk, what we found to work quite well is to look at embedding similarity again. So instead of looking at success on the y-axis as measured by hardware evaluations, we construct these curves, these scaling curves, by looking at embedding distances. And the rest of the analysis is identical. So we construct the curves, we extrapolate them, and then we rank them by the greatest kind of predicted improvement in performance. And I think what we found, somewhat surprisingly maybe, is that we're able to basically recover the performance that we get when we construct the scaling curves with real hardware evaluations. So for 3 out of the 4 tasks here, the factor that is chosen to be prioritized when you do this kind of embedding similarity analysis is the same factor that we prioritize when we do real hardware evaluations. There's one task here where there is some difference. But yeah, I guess the kind of cool thing here is that there are no hardware evaluations to predict or to construct the scaling curves. There's still some cost in setting up the environments. And I guess that's where kind of the image editing work can come in again. But yeah, it's neat that we're able to make these scaling curves and make strong predictions without doing hardware evaluation. So yeah, maybe just to conclude, I guess maybe we can discuss this in the panel. In our group and then other groups as well. There's been lots of work on trying to find algorithmic solutions to OOD generalization. But I think there's been remarkably little progress. And the thing that has worked kind of over and over again is adding data. And the work that I presented today uses progress in OOD detection. So there's been a bunch of progress, including kind of from people in the room. But to use these techniques like kind of embedding based analyses and so on to figure out what looks anomalous to your policy, and then to use that to guide data collection, collect that data, fine tune your policy. And that seems like a kind of reasonable recipe to get out of distribution generalization. And I think that the dream, for me at least, is some kind of fully automated and offline pipeline for finding the vulnerabilities of your policy. So ideally, you want to just upload your policy checkpoint. There's some kind of fully offline process that runs and gives you a report card saying these lighting conditions might be bad for your policy is good with distractors, and so on, which can then guide additional data collection to help you with OOD generalization. So yeah, I think that's all I had. I'll stop here and take more questions.
Yeah, so the factor scaling curves is really cool. It feels almost like you're finding like a gradient of the performance with respect to some variables. So have you considered like instead of just following those axes, like following like some vector of like some different coordinate shift almost?
Oh, interesting. Yeah.
Like I know that'll end up meaning more like hardware setup work, but I was wondering if
Yeah.
you do some like SVD and see like what the
Yeah.
actual.
Yeah, I think we've done that heuristically a little bit, where we've grouped different factors together. But I think what you're suggesting is more interesting, where you figure out the grouping kind of automatically. It's not just like scaling along one dimension. Yeah, maybe I should change this factor and this factor and this factor by different proportions. One idea would be so I mentioned this work that looks at weights on your data.
Yeah.
There's a bunch of work actually looking at data curation.
Yeah.
I think we could probably do similar scaling analyses there. Like you do this kind of weighting thing for multiple checkpoints that scales data along different axes and try to extrapolate that. And maybe that will tell you what mixture of data I should go out and collect. Yeah, we haven't really done that systematically, but I think it's super interesting.
Thank you.
Yeah, it sort of requires you to like list out everything that can go wrong. And they seem to be like independently lighting may matter or distractors may matter, but in reality, it could be a combination of things that really matter.
Yes.
Have you thought about maybe like automatically generating what can go wrong rather than having someone list out everything that can go wrong? Because that might be tough.
Yeah, definitely. I think the next step, or I guess one next step along the red teaming direction would be to automate it somewhat and have like an iterative scheme where you start with some analysis of like this factor is going to be important, that factor is going to be important, and then kind of make guesses based on that to further probe the vulnerabilities of your policy. With these image editing models, it's actually very straightforward to change multiple factors simultaneously. So if you have some initial guesses for what might degrade performance, then you can start looking at combinations of those, and have some kind of iterative process that figures out like what's the weirdest combination for your policy that's going to degrade performance.
Do you think that could lead to less data if you just combine everything bad into one thing and then you don't need the individual ones?
It could lead to less data that you need to collect. Yeah, like maybe if you find the right combination of things. I guess this goes back to the previous question as well. Like if you find the right combination of things to vary, you might have to collect much less data because you're varying things simultaneously.
I had a question. I think there was an example where you had the graphs and showing the progress of your method, but there was like one specific, I think it was like the folding towel test that saw like an anomaly where there's like a drop off in performance.
Yeah.
And then I think that there was another slide where you had like predictions of like success rate, and then there was like one specific
Oh, yeah.
red square.
Sure.
Do you have any insight for like
Yeah, yeah.
why these kind of like
Yeah.
fell out of distribution?
Yeah, so I think the other one, part of it is real hardware evals are hard. And that's something I learned. I mean, I guess in hindsight it's maybe obvious, but often we don't do the hardware evaluations like super systematically. Like we should be doing like A/B testing and things like that. If we're comparing things, like trying to make sure that as many factors are controlled as possible, and you're only changing one thing. So I think some of that in the other plot, maybe I can pull it up. One of these, I think. Yeah, there's some. This green lighting one, for instance, is much further away. I think some of that is noise and hardware evaluations. We were doing like 20 experiments, and I guess some of it is just like there's a lot of coarseness in this like embedding based similarity metric. Like we're relying on the distances in embedding space being predictive of like actual performance, which they're not necessarily, right? It's just a kind of coarse predictor.
Great, thank you.
A lot of questions I can think about.
Oh, okay, yeah. We also have a panel that Ani's gonna be on, which is starting now. So we will have a Slido up. You can put up your questions generally for that as well on the Slido. So, okay, let's thank Ani one more time.